Welcome back, ladies and gentlemen. So let's see what are we going to discuss in this week's class. Before we begin, do you guys have any questions on last week? Can everyone see the slides? That's good. I just saw a raised hand flash by my screen, but it happened so fast I didn't see who it is. But you're more than welcome to ask your question. Yes, Mr. Fisagi.
Professor, I was just curious. On Thursday's lecture, you're talking about with Linux and the scientific Linux and the Hadron Collider. If the small particles have any relationship with how the universe functions.
Yes. So there's another branch of astronomy if you guys are interested in it. You will touch on it in third year, but that's another field of expertise where you look at astrophysical particle physics. So to look what happens with particles radiating from objects in space. So some of these particles are particles being ejected from different stars. So we have neutrons that we can detect from space because neutrons move through basically anything. So we have detectors underground for them. And we need to know how these particles interact in space to understand magnetic fields and electric fields around objects, because every object forms part of the electromagnetic spectrum and therefore has a magnetic and electric field. So we need to understand how these electromagnetic fields is working. So one example of how we study these particles in everyday life in astronomy is if we look at different objects, we look at their polarization. So if you're not familiar with polarization, if you buy sunglasses, you'll sometimes see your sunglasses is polarized. So if you take your polarized glasses and you put it in front of a electronic screen such as a computer screen, cell phone screen, and you turn your glasses 90 degrees, then the screen will blacken out. So it means the polarization only lets light through in a certain way. So it's going to be easier getting the whiteboard out again. So usually when you have a polarization, it happens in one of three ways in astronomy. So 3D glasses is an example for it, yes. So in 3D glasses, both lenses are polarized in different ways. So if we have a source of electromagnetic radiation, an example of this can be the sun. Then we usually have a polarization filter. So it can either look just polarized vertically, where it has these slots where the electromagnetic radiation can go through, or it can be vertically polarized. And by using polarized, or the third one we use in astronomy is circular polarization. And by making use of these polarizations, we can see what the magnetic fields are doing around objects. So this is one way how we study the magnetic fields around our own sun. And if you look at the definition what a magnetic field is, magnetic fields is particles moving around an object. So you're looking at electron movement around an object. But if you have electron movement, then you have an electric field and a magnetic field that is 90 degrees to each other. So what I mean with 90 degrees, Let me just clear this whiteboard. So if we have one wave going this way, just a normal sinusoidal wave, and then we have our axis, so axis, so this is y, this is x. Then this plane we will have another axis, and that is our z-axis. So let me try and draw this correctly without screwing this up. Then we will have another wave going along this axis, and the angle that these two waves make with one another is 90 degrees. And then with this as well, we determine what other particles we can determine, because we are, so all the particles that the Large Hadron Collider detects is also created in phenomena in space, such as Big Bang, two objects hitting one another, objects going supernova, burning of certain types of fuel. Another way where particle physics is important in astronomy is by observing black holes, because in a black hole, the only thing we can see is really the event horizon. So we look at X-rays going around the event horizon. So I hope that answers your question. So how's my research going? My research is going on. I just have a bit of a software snag at the moment. So how we know if we watch the recorded lecture after? Sometimes we have a math test at the same time as the lecture. So please let me know if you have a math test at the same time as the lecture. Other modules is not supposed to schedule tests in other modules time slots. So please let me know so I can sort out that problem. But the recorded lectures are available on Blackboard Collaborate. Yes, Ms. Niemand.
So not next week. No, wait, it is next week. Next week, Monday, is a public holiday. And I'm not sure if we're going to have Monday lectures on Thursday again. If we are, we're going to have another clash because we're writing for the same module. We're writing a test again on Thursday at 5. So I don't know if there's something like we need to do about that, but I was just, because you're talking about it, I just wanted to say.
Oh, thanks for letting me know, Ms. Niemand. I will find out from the department how the time schedule is going to look like and what's going on, and then I will report back to you guys tomorrow evening. So coming back to the comment, how do you look for the lectures? So in Blackboard Collaborate, so there's a, before you join the session, on the left-hand side, there will be a button you can click. All the recorded sessions are there. I also uploaded to Google Drive. So if you connect through the UP Connect portal and download them from Google Drive, there won't be data costs. And I also upload them to YouTube. Okay, so, okay, cool. So let me go back to our slides and we can start with tonight's lecture. So in the previous lectures that we've done, we had a brief overview of what this module is going to be about, and we discussed a few interesting topics, but now we're going to start from the beginning and go in depth on different objects we're going to discuss in this course. But before we can do all the fun stuff, such as planets, stars, black holes, modern astronomy, we first need to understand the basics. And the basics is, where does astronomy come from? So the history of astronomy. And then we need to understand how a telescope works and what are the basic components of a telescope. So in tonight's lecture, we are going to look at the origin of modern astronomy, classical astronomy, and Newtonian astronomy. So does anyone know the difference between these three? Yes, Mr. Levuyo.
So I'm not 100% sure, but I'm going to try.
Okay, cool.
So Newtonian astronomy, so I'm assuming that was astronomy made in, when Isaac Newton discovered the laws of motion, and then the laws of motion predicted uh, the planets quite well, except for Mercury.
Yes.
Classical astronomy, I'm assuming it's before Newton. I don't know if Newton and Galileo were there at the same time or before or after, but I think that was when Galileo first discovered the three moons around Jupiter with Kepler's laws, I think. And
Yes,
then
you are spot on.
and then the origin of modern astronomy, I'm assuming this is Einstein's time when he came up with the is it special his theories of special relativity and general relativity.
Yes. Yes, you are spot on. So, before we get to the origin of modern astronomy as we know astronomy of today, we need to look at classical astronomy from Galileo Galilei, that's a bit before Newton, and then we get to Newtonian astronomy, where we look how Newton's universal law of gravitation come into effect, and also Kepler's laws and how it describes how these objects are moving. So I like to open up tonight's class with the following quote from famous astronomer Carl Sagan. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. So are you guys all familiar with Carl Sagan? Not really. You can tell me a bit about Carl Sagan. Yes, he hosted the original Cosmos. Yes, he did it before Neil deGrasse Tyson. He was a professor at Cornell University. And yes, he is one of the founders of the SETI program, so Search for Extraterrestrial Intelligence. So how did humanity first realize that we live on a planet moving through space? That required a revolutionary overthrow of an ancient and honored idea of Earth's place. By the 16th century, many astronomers were uncomfortable with the theory that Earth sat at the center of a spherical universe. So, three of the most important figures in astronomy are Nicholas Copernicus, Galileo Galilei, and Sir Isaac Newton. What do you guys know of Nicholas Copernicus? Yes, Mr. Levuyo.
So was he not the first to hypothesize that the Earth wasn't the center of the universe?
Yes, so he was one of the persons that theorized that we move in circles in orbit around each other. And then Galileo Galilei.
So did he created the first telescope, reflective telescope?
Yes, so not invented it, but improved their telescope. And then we are all familiar with Sir Isaac Newton. So something interesting, if you go to London, there you will find, don't remember where in London it is. I want to say Westminster Abbey, but I think I'm wrong. But then you can find the tomb of Sir Isaac Newton. So for this chapter we are looking at tonight, we are going to discuss four important questions. How did classical philosophers describe Earth's place in the universe? How did Copernicus revise that ancient concept? Why was Galileo condemned by his Inquisition? And how did Isaac Newton change humanity's view of nature? Okay, cool. So this is Westminster Abbey. So, astronomy is the only progressive science which the ancient world produced, and that is from William Whewell. How you would burst out laughing, my dear Kepler, if you would hear what the greatest philosophers of the gymnasium told the Grand Duke about me. That's a letter from a letter by Galileo Galilei. As early civilizations developed, great philosophers struggled to understand the movements of the sun, moon, and planets. Later mathematical astronomers made precise measurements and computed detailed models in attempts to describe celestial motions. It too took hard work and years of effort, but the passion of astronomy gripped some of the greatest minds in history and drove them to try to understand the sky. Yes, you are correct about Stephen Hawking as well. The first theme we will investigate is the struggle to understand the place of Earth in the universe. It seemed obvious to the ancients that Earth was the center of everything, but today, you know that is not true. The debate over place of Earth involved deep theological questions and eventually led Galileo before the Inquisition. So let's jump back a few thousand years. So, without the knowledge that we have today, if you look at the night sky, what would you think? Would you believe that we are moving around objects, such an orbit around the sun, or would you believe everything is moving around us? So let's get into the mindset of the early astronomers, where everybody thought things are moving around us. How do you get into the mindset and determine of how is we moving around everything? Then a second theme is we will investigate a long and difficult quest to understand planetary motion. Astronomers built more and more elaborate mathematical models, but they still could not predict precisely or explain the motion of the visible planets along the ecliptic. That mystery was finally solved when Isaac Newton described gravity and orbital motion in the late 1600s. The great philosophers of ancient Greece wrote about many different subjects, including what I saw in the sky. Those writings became the foundation on which later astronomers built modern astronomy. So we have the Aristotelian universe. So do you guys know who these two characters is?
Is the Aristotle.
Yes, that is. And the other one is Plato. Yes. So before in astronomy world, and even in every other science, we need to set up first principles. So first principle is something that is held to be obviously true. Once a principle is recognized as true, whatever can be logically derived from it must also be true. So what first principles can you guys think of? Yes, differentiation is a very good example. What else can you guys think of as a first principle? Newton's laws are also first principles. Logarithms are first principles. Exponents are first principles. Universal constants as well. So for 2000 years, the minds of astronomers were shackled by a pair of ideas. The Greek philosopher Plato argued the heavens were perfect because he considered the only perfect geometrical shape to be a sphere, and turning spheres carries a point on its surface around in a circle, and because the only perfect motion is uniform motion, Plato concluded that all motion in the heavens must be made up of combinations of circles turning at uniform rates. This idea was called uniform circular motion. So the entirety of algebra, not the entirety of algebra. So what do we mean when we say first principles? So first principle is if we go back to the basics of something, you cannot simplify it more. And the principle will state something is something, and that is absolutely true. Under every circumstances, that holds up and that is true. So if you use that principle in somewhere else, then that also implies that that must be true, if that answers your question. So Plato's student Aristotle argued that Earth was imperfect and lay at the center of the universe, such a model known as the geocentric universe. His model contained 55 spheres, turning at different rates and at different angles to carry across the sky the 7 celestial objects called planets. So the Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn. The question, is there a relationship between Fibonacci and uniform circular motion? That I don't know. I will find out and I will report on that tomorrow evening again. Aristotle was known as the greatest philosopher in the ancient world, and for 2000 years his authority limited the imaginations of astronomers to uniform circular motion and geocentrism. So here we can see Aristotle's universe. So, looking at the Aristotle universe, have you guys ever thought of how do we determine the distance to something in space? So one of the methods that we used and that the ancient astronomers came up with is called parallax. So somewhere in your high school career, you probably heard about the parallax fault. So one way to do it, you guys can do it now. So if you stretch your hand out in front of you, you cover your thumb with an object you're looking at that's far away. Close your left eye, and that's what you're going to see. So keep your thumb on the same object. If you close your left eye and open your right eye, this is what you will see. So you'll see there's a slight difference in angles that your eyes see the object on. And that angle that differs is called the parallax. So early astronomers believed that Earth did not move because they saw no parallax, the apparent motion of an object caused by the motion of the observer. So we did a demonstration of parallax. So if Earth moves, they reasoned, you should see the sky from different locations at different times of the year. And you should see parallax distorting the shapes of the constellations. They saw no parallax, so they concluded Earth does not move. Actually, the parallax of the stars is too small to see with the unaided eye. So every 2.14 years, Mars passes through a retrograde loop. Two successive loops are shown in the next picture. So each loop occurs farther east along the ecliptic and has its own shape. Simple uniform circular motion centered on Earth could not explain retrograde motion. So ancient astronomers combined uniformly rotating circles, much like gears in a machine, to try to reproduce the motion of planets. So what retrograde is, because we have our, let me get out the whiteboard so to describe it easier. So let's go through the figure first before I try and draw it. So here on the red line we have the ecliptic, and Mars' orbit is larger than Earth's orbit. So every 2.14 years, there's a point where Earth and Mars will pass one another. So let's go in the 2016 model. So here we have the problem. So let's go through it. So planetary motion was a big problem for ancient astronomers. In fact, the word planet comes from the Greek word wanderer, referring to the eastward motion of the planets, including the moon and sun, against the background of fixed stars and constellations. The planets do not move, however, move at constant rate, and they could occasionally stop and move westward for a few months before returning to this motion. This backward motion is called retrograde. So what happens is so here is the ecliptic, we have the suns, we have Mars coming. So it comes to a point where Earth and Mars is next to each other. And then because Earth is in a smaller orbit than Mars and moves past, it would seem that Mars is moving westward again and then moving eastward again. So Mars isn't really doing it. It is just because we are orbiting faster around the Sun than Mars. And in 2.14 years later, the exact same thing happens. Does everyone understand retrograde motion? Is that a point when they are closest to each other? So yes, that as well. Do you guys want me to explain it in a different way? Okay, so let me try and explain it a bit better. So let me see if I can explain it better. So with retrograde motion, we have our ecliptic, and it's moving from east to west on this line. But if we look at the solar system, we have Earth's orbit. What happened now? Let me draw it again. So first, to explain it, let's say this is the sun. We have Earth's orbit, and we have Mars's orbit that is larger. So then we have the ecliptic. So the best way is the ecliptic is the line in the sky on which we can call it the imaginary line in the sky on which the planet moves. That is called the ecliptic. So let's get another color out. So let's say, for example, this is Earth, this is Mars. Then a few months later, we have Earth and Mars, so the distance is smaller. Then we have Earth, we have Mars. Then we have Earth and Mars. Then we have Earth and Mars. So in this motion where Earth moves faster around its orbit because the orbit is smaller than Mars, on the ecliptic we will see a motion that Mars will be doing something like this. So it moves eastward, eastward, eastward. Then suddenly, when Earth moves past it, it will appear that its orbit is going back again, and then this way again. And then 2.5 years later, when the Earth and Mars is together, then we will have the same principle again, where we will have Mars and Earth directed to each other, and when Earth passes Mars again, it will look like it's moving backwards again, and then it will look like it's going forward again. But in fact, it's not moving backwards, it's just our perspective from Earth. Or is it still a bit too complicated? So I think my sketch is not one of the best sketches. Okay, cool. So if we go back to our slides, so here we will see these are the different locations of Mars. So here at this point at April 16th, Earth and Mars will be next to each other. Then from here, Earth will start going, because its orbit is smaller, it looks like we are overtaking Mars, and it would look like Mars is going in the opposite direction. Then we'll continue forward to the point, and then 2.14 years later, this happens again. So does retrograde motion only happens with Earth and Mars? No, it happens with the other planets as well. So we have retrograde motion with all the planets that is in orbits closer to the Sun. So we will have retrograde motions with Venus as well and with Mercury as well. But Mars's retrograde motion is easier to see because Venus and Mercury's orbits are so close to the Sun. We can only basically see Venus and Mercury if the Sun is rising and when the Sun is setting. So we have only a short window to observe those planets. So in this window, it's difficult to see retrograde motion, where Mars, we can see basically throughout the year, any time of night. So then retrograde motion will be easier to see. So, say for example, we are on Mars, then we will have retrograde motions with Jupiter as well. If we are on Jupiter, then we will have retrograde motions with Saturn. So it's a common phenomena in space. So uniformly rotating circles were key elements of ancient astronomy. Ptolemy created a mathematical model of the Aristotelian universe in which the planets followed a small circular called the ecliptic that slid around a large circle called a deferent. By adjusting the size and rate of the rotation of the circles, he could approximate the retrograde motion of a planet. So we can see it in illustration on the right. So to further adjust this model, Plot added small circles, so not shown here, riding on top of larger epicycles, producing a highly complex model. So Ptolemy's great book, Mathematica Syntaxis, published around the year 140, contained the details of this model. Islamic astronomers presented and studied the book through the Middle Ages. They called it Al-Majesteri, the greatest. When a book was translated from Arabic to Latin in the 12th century, it became known as the Almagest. The Plotic model of the universe shown was geocentric and based on uniform circular motion. So note that Mercury and Venus were treated differently from the rest of the planets. The centers of the epicycles of Mercury and Venus had to remain on the Earth-Sun line as the Sun circled Earth through the year. Equants and smaller epicycles are not shown here. Some versions of the model contained nearly 100 epicycles added by generations of astronomers trying to fine-tune the model to better reproduce the observed motion of the planets. So notice that this modern illustration shows rings around Saturn and sunlight illuminating the globe of the planets, features that would not have been known before the invention of the telescope. So here we can see a perfect illustration of it. And then we start touching on the Copernican revolution. You would not have expected Nicholas Copernicus to trigger a revolution in astronomy and science. He was born in 1473 to a merchant family in Poland. Orphaned at the age of 10, he was raised by his uncle, an important bishop, who sent him to the University of Crawshaw, and then to the best universities in Italy where he studied law and medicine. Nevertheless, he had a passion for astronomy even as a student. Somewhere between 1514, he wrote an essay proposing a model of heliocentric universe, in which the Sun, not the Earth, was the center. So, question here, do you know when all the planets will align again? I'm not sure about that. I will also report back on that tomorrow evening. In the Copernican system, Earth moves faster along its orbit than the planets that lie further from the Sun. Consequently, Earth periodically overtakes and passes these planets. To visualize this, imagine that you're on a race car driving rapidly along the inside lane of a circular racetrack. As you pass slower cars driving in the outer lanes, they fall behind. And if that did not realize you were moving, it would look as if those cars in the outer lane occasionally slowed to a stop and then backed up for short intervals, so retrograde motion. So here we can see another representation of retrograde motion. Copernicus could explain retrograde motion without epicycles, and that was impressive. The Copernican system was elegant and simple compared with the whirling epicycles and off-center equants of the Ptolemaic system. However, the revolutionists failed in one critical way. The Copernican model would not predict the positions of the planets significantly more accurate than the Ptolemaic system could. Copernicus proposed a revolutionary idea that made the planetary system heliocentric, but he was a classical astronomer with tremendous respect for the old concept of uniform circular motion. In fact, Copernicus objected strongly to Ptolemy's use of the equant because it required that the planet move faster in some places and slower in others. It seemed arbitrary to Copernicus, an obvious violation of uniform circular motion and the elegance of Aristotle's philosophy of the heavens. Copernicus called equants monstrous because they undermined both geocentrism and uniform circular motion. In devising his model, Copernicus demonstrated a strong belief in uniform circular motion. Although he did not need epicycles to explain retrograde motion, Copernicus quickly discovered that the Sun, Moon, and planets suffered another small variation in the motions that he could not explain using uniform circular motion centered on the Sun. Today, astronomers recognize that those variations are the result of planets following slightly non-circular elliptical orbits. But because Copernicus held firmly to uniform circular motion, he had to introduce small epicycles to try to reproduce these minor variations in the motions of the Sun, Moon, and planets. The Copernican model is inaccurate. It includes uniform circular motion and consequently does not precisely describe the motion of the planets. But the Copernican hypothesis that the universe is heliocentric is correct, considering how little astronomers of the time knew of other stars and galaxies. The universe that Copernicus knew was heliocentric in that the planets circled the Sun and not the Earth. So in this figure, the Copernican universe was elegant in its arrangement and its motions. Mercury and Venus are treated like all other planets, and orbital velocities, so blue arrows, decrease smoothly from that of Mercury to the fastest, that of Saturn, the slowest. Compare the elegance of this model with the complexity of the Ptolemaic model shown in the previous figures. The Copernican hypothesis solved the problem of the place of, but it didn't explain planetary motion. If planets don't move in uniform circular motion, how do they move? The puzzle of planetary motion was solved during the century following the death of Copernicus through the work of two men. One compiled the observations and the other did the analyses. So the planets are not equidistant from one another. So, do you guys know who these two men is that we're going to discuss next? So one did the observations and the other one the analysis. So, the first is Tycho Brahe. Although Tycho officially studied law at a university, his real passion were mathematics and astronomy. And early in his university days, he began measuring the positions of planets in the sky. In 1563, Jupiter and Saturn passed very near each other in the sky, nearly merging into a single point on the night of August 24. Tycho found that the Aufstein tables were full month in error and Prutenic table were in error by a number of days. So these tables were used to predict where the planets will be in the future. In 1572, a new star, now called Tycho's supernova, appeared in the sky, shining more brightly than Venus, and Tycho carefully measured its position. According to classical astronomy, the new star represented a change in the heavens and therefore had to lie below the sphere of the moon. Tycho, even though he believed in geocentric universe, understood that. So we came up with the tables. We're going to discuss that chapter as well. The new star should show parallax, meaning it would appear slightly too far east as it rose and slightly too far west as it set. But Tycho saw no parallax in the position of the new star. So he concluded that it must lie above the sphere of the moon and was probably on the starry sphere itself. This contradicted Aristotle's conception of the starry sphere as perfect and unchanging. No one before Tycho could have made this discovery because no one had ever measured the positions of celestial objects so accurately. Tycho had great confidence in the precision of measurements, and he had studied astronomy thoroughly. So when he failed to detect parallax for the new star, he knew it was important evidence against the Ptolemaic theory. He announced the discovery in a small book, De Stella Nova, so the new star, published in 1573. And then you are right, the next guy is Johannes Kepler. So, are you guys all familiar with Kepler's three laws? Okay, so we'll discuss. So, just a question. I assume those of you that's familiar with Kepler's laws did this in physics high school, or was that removed from the syllabus? Oh man, because I remember I did Kepler's three laws when I was in high school. But Kepler's three laws is something you will use or learn about a lot in your other modules. I know you will do Kepler's law, especially in your introductory to physics modules and especially in your classical mechanics modules. But you will also use Kepler's laws in applied mathematics as well. So let me explain those three laws. If you don't understand something, please stop me so I can try to explain it to the best of my abilities. But overviews is the first law is the orbits of the planets are ellipses with the sun at one focus. The second law, a line from a planet to the sun sweeps over equal areas in equal intervals of time. And the third law, a planet's orbital period squared is proportional to its average distance from the sun cubed. So let's go through these laws slowly. So the first law of Kepler, so these laws are very important for planetary motion. So Kepler's first law, each planet orbit around the sun is ellipse. The sun's center is always located at one focus of the orbital ellipse. The sun is at one focus, the planet follows the ellipse in its orbit, meaning that the planet to the sun distance is constantly changing as the planet goes around its orbit. So visualizing this, it will give us this. So as we can see here, this is a ellipse. Because it's an ellipse, we will have a focus on one side, we have a focus on the other side, but the sun will be at one focus, and the planet will move around it. So all planets move about the sun in elliptical orbits, having the sun as one of the foci. So does everyone understand this concept? Yes, Kepler was an astronomer and mathematician. Okay, so you guys are comfortable with the first law? It's not because the center of mass shifts, but it is because The best way I can describe it is we as humans like things to be perfect. So we like things to be linear, we like perfectly symmetric circles, but in nature we don't have perfectly symmetric circles and we don't have anything linear. So it depends on how it's formed and how the gravitational pull of the star is working, but everything will be in ellipses. Before going on to second law, is everyone comfortable with the first law? Okay. So Kepler's second law. Could you just give a bit of a recap? So recap on the first law. That what you mean? Okay, so let's go back to the slide. So recap on the first law of planetary motion and Kepler's laws is the first law is planets will move in a ellipse around the sun, where the sun will be at one focus of the ellipse. So Kepler's second law, the imaginary line joining a planet and the sun sweeps equal areas of space during equal time intervals as the planet orbits. Basically, that planets do not move with constant speed along their orbits, rather their speed varies so that the line joining the centers of the sun and a planet sweeps out equal parts of an area in equal times. The point of nearest approach of a planet to the sun is termed perihelion. The point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is perihelion and slowest at aphelion. So, putting this in a perspective, here we have our ellipse and our planet moving around. So here we can see we have the sun at one focus. So if you would use the other focus, it would be around about there, but we only use one focus. So it means if we divide this into area, we have this area 1 and this area 2. So the distance covered in 1 month, so from this point to this point, so the area we have must be the same area on this side, so 1 month. So that means when the sun is at perihelion, so that means its closest approach, yes, this affects seasons a little bit, but seasons are more affected by the cant of the Earth. So that means with this point nearest approach of the planet, so the perihelion is over here, and then the furthest separation is the aphelion. So that means, we put this in perspective, the fastest will be a perihelion, moving this over here, and the slowest will be at aphelion. So what causes the change in speed is gravity. So here, no, we are not tidally locked with the sun. So if we are further away from the sun, like over here, it means we have our distance a bit further away, meaning the gravitational pull is a little bit lower, meaning our speed will also be a little bit lower. Coming to the other side, when we are at perihelion, we are closer to the sun, meaning our gravitational pull is stronger and our speed is faster. So another way to explain this, are you all familiar with a slingshot maneuver in space? Okay, so let me get the whiteboard out. So all of the sci-fi fans will know what a slingshot maneuver is. So for me, before explaining or drawing it, is there any volunteers that want to explain what a slingshot maneuver is? Yes, Mr. Levuyo.
Gravitational slingshot says basically when a small object takes advantage of the strength of the gravity of an object. So, for example, say you have the sun. The sun is a very huge, enormous object with a large gravity. And so, if you had to be on a spaceship or space shuttle, that's very small compared to the sun. So, if you had to fly very close to it, and then, if I'm not mistaken, you had to fly at an angle, the momentum of the the space shuttle will increase because the energy from the gravitational from gravity has pulled it, so then it can like sort of, I want to say, throw it away. I'm not sure of the terminology, but I think that's the idea.
Yes, that is completely correct. Thank you, Mr. Levuyo. So if I draw a slingshot maneuver, let's say this is the sun, it can be a star, it can be a planet. That object has a gravitational pull. So if you have an object moving towards it, so let's say a spaceship, for example, then you use energy to go to that object, but you make sure your approach to that object, so your angle, is completely correct. So when you approach the object, you will not end, so if your angle is, I want to say, too steep, then you will get caught in the gravitational pull and you will be lost into the object. If your angle is too shallow, you will be bounced off it. If your angle, let's get a different color, if your angle is precise, then you will be caught in a gravitational field and put into a stable orbit. But if you calculated this just right, you will come close to the object, you will get up momentum, then have enough momentum to break through the gravitational field, and that will slingshot you into a different direction at a much faster speed than possible when approaching it. So when we send out spacecraft to our solar system, for example, we send a probe to Jupiter or Cassini sent to Saturn, we usually do a slingshot maneuver around a different planet or object to get enough momentum to get to our destination. So there's, you can Google it, there is the Super Galactic Highway. And that is the path with the least amount of energy to get in the solar system. And that's by making use of slingshot maneuvers. So in Kepler's second law, let me just clear the whiteboard. We have the sun at one focus. We have our ellipse around the sun. So when we are moving around here, we are much closer. That means the gravitational pull is pulling us closer towards the star, but we are not pulling into it, so that means we are slingshotted this way. So here we lose a little bit of momentum. We are pulled back to the star or sun, and here we are gaining momentum again. But if we draw this in areas, so we call this area A1, and we call this area A2. So we know A1 equals A2. So we know the speed, or under speed, the time to cover this area of A1 is the same time to cover this area of A2. So if this is, that's a horrible handwriting, 1 month, we know this side must also be 1 month. So it means in area A2, we are moving faster. In area A1, we are moving slower. So do we know where we could find the derivation of that formula? If you Google it, you will find many papers on it. So question, could a slight shift as in a few kilometers closer to the sun cause for Earth to be pulled into the sun, or is that a bit too drastic since it seems that we are at equilibrium point with the sun? So a few kilometers wouldn't make a difference, but if we go to a few hundred kilometers, that will make a big difference. We will not be pulled in, but that will cause a big difference on the temperature we have here on Earth. For example, the distance from Earth to Mars is roughly 0.7 AU, so a bit more than half AU. So AU is 150 million kilometers. So a bit more than half, we can say it's roughly 90 million kilometers as distance from Earth and Mars. So Earth and Mars are in the Goldilocks zone around the sun. So on Earth, we have quite nice temperatures. So take, for example, our average room temperature around the globe is roughly 24 degrees. But if you go to Mars, the average temperature around the globe is sitting at minus 60 degrees. So that is the difference that 90 million kilometers makes. So, say for example, we are 90 million kilometers closer to the sun, then our temperatures will be much, much warmer. Something a bit off topic, but interesting. Did you guys know that the temperature scale is not linear? So meaning not linear, if you look at Celsius, so you cannot say 4 degrees Celsius is twice as warm as 2 degrees Celsius. Yes, it's logarithmic. So if you look at a Celsius scale, it will look something like this. So 1 degrees, 2 degrees, 3 degrees, 4 degrees, 5 degrees. So let me just draw the axis on. So that is the Celsius scale. So we cannot say 4 degrees is 2 times as warm as 2 degrees. And the same principle applies to degrees Fahrenheit. That's why we like to use Kelvin in science, especially astronomy, because the Kelvin scale is linear. So here we would have, so here we will have temperature, and here we will have magnitude. But if we look at our Kelvin scale that we like to use in astronomy, Kelvin is nice and linear. So in the Kelvin scale, we can say that 4 degrees Kelvin is twice as warm as 2 degrees Kelvin. And 8 degrees Kelvin is twice as warm as 4 degrees Kelvin. And 1 degree Kelvin is minus 273 degrees. So putting it that way, that is correct. So absolute zero is minus 273 degrees Kelvin. So just to give you importance of why this is important, electronics causes noise on our equipment on telescopes. We pick up the electrons from these telescopes. So to get that electric noise out, we try to cool our equipment. So we speak of that equipment as receivers, or our CCD sensors as cold as possible. So in astronomy, usually it's kept at around about 12 degrees Kelvin, so that is more or less minus 260 degrees. No, there are no negative Kelvin temperatures. The coldest thing we have is absolute zero, and that is 0 Kelvin. Nothing in the world can be colder than absolute zero. So I think there's another comment that I missed somewhere. I'm just scrolling up. There was something that someone said about Voyager. So yes, was the slingshot used back in the Voyager mission to explore the system? Yes, Voyager used the slingshot maneuver. And how possible is it to use the slingshot to get out of our solar system? Yes, the slingshot maneuvers is exactly what we need to build up momentum to escape our solar system. So yes, you lost the screen. I'm just going back to the slides. Let me go a bit more slides. I'm just trying to find a slide that we were on. So here we are back at the slides. So question, why wouldn't the Earth be slingshot out of the solar system? That is because we are in such equilibrium that the momentum we build up is not enough to escape the gravitational pull of the star, of our own sun. So this is Kepler's second law. So everybody now comfortable with Kepler's second law? Yes, so all the probes use some sort of slingshot maneuver. So for example, when the Perseverance rover was sent to Mars, it wasn't just fired up and then was pointed to Mars and there we go. It first did a few orbits around Earth to build up momentum, as it basically did a slingshot maneuver around Earth and then went on to Mars. So Kepler's third law, the squares of orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits. Kepler's third law implies that the period of a planet to orbit the Sun increases rapidly with the radius of its orbit. This we find that Mercury, the most innermost planet, takes only 88 days to orbit the Sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. Though Kepler hadn't known about gravitation when he came up with these three laws, they were instrumental in Isaac Newton's deriving his theory of universal gravitation. It explains the unknown force behind Kepler's third law. Kepler and his theories were crucial in the better understanding of our solar system dynamics and as a springboard to newer theories that more accurately approximate our planetary orbits. So here, the third law only implies the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distance from the planet. So here we can see the orbital periods of the different planets. So yes, these formulas will be given to you in the test. There's no need to memorize these formulas. So to put the third law in perspective, the closer we are to the object we are orbiting, the faster the orbit will be. The further we are away from the object we are orbiting, the slower the orbit will be. Is anyone comfortable with the third law? Okay. Does everyone have questions before we continue to the next slide? Repeat the third law. Okay, so the sweet and short of the third law is, if we are orbiting an object, the closer we are to the object, the faster our orbit will be. The further away we are from the object, the slower our orbit will be. Awesome. So, we mentioned the tables used before. So the first are the Rudolphine tables. The Rudolphine tables was Kepler's masterpiece. It could predict the positions of the planets 10 to 100 times more accurately than previous tables. Kepler's tables were the precise model of planetary motion that Copernicus had sought but failed to find. The accuracy of the Rudolphine tables was strong evidence that both Kepler's laws of planetary motion and the Copernican hypothesis of the place of Earth were correct. And now we get to Galileo Galilei. Most people think they know two facts about Galileo, but both facts were wrong. They are common misconceptions. You have probably heard them. Galileo did not invent the telescope, and he was not condemned by the Inquisition for believing the Earth moved around the sun. Then why is Galileo so famous? When did the Vatican reopen his case in 1979, almost 400 years after his trial? As you learn about Galileo, you will discover that his trial concerned not just the place of Earth and the motion of the planets, but also a new and powerful method of understanding nature, a method called science. The telescope was apparently invented around 1608 by lens maker Holland. Galileo, hearing descriptions of the fall of 1609, was able to build telescopes in his workshop. In fact, Galileo was not the first person to look at the sky through a telescope, but he was the first person to apply telescopic observations to the theoretical problem of the day, the place of Earth. What Galileo saw through his telescopes was so amazing that he rushed a small book into print. Sirius Nucius, so translated the story messenger, reported three major discoveries. First, the moon was not perfect. It had mountains and valleys on its surface. And Galileo even used some of the mountains' shadows to calculate their height. Aristotle's philosophy held that the moon was perfect, but Galileo showed that it was not only imperfect, but was a world with features like Earth. So just a little tip I can give you for the test and exam. So seeing that I have a lot good participation in tonight's class, I can give you a tip the slide we are on are important for the test and exams. Pleasure. So the second discovery reported in the book was the Milky Way was made up of myriad stars too faint to see with the unaided eye. While intriguing, this could not match Galileo's third discovery. Galileo's telescope revealed 4 new planets circling Jupiter, objects known today as the Galilean moons of Jupiter. The telescope was apparently invented, we did saw the sky, we did do the slide, sorry, it just looks like, okay, no, we didn't do this. So the telescope was apparently invented around 1608 by lensmaker, yeah, we did a spell out. What Galileo saw for his telescope was so amazing, he rushed. Okay, we did do this paragraphs of some reason, sorry, I copied us both. So the second discovery reported in the book was that the Milky Way was made of myriad stars. We did a, so Galileo's telescope revealed 4 new planets circling Jupiter, objects known today as the Galilean moons of Jupiter, and keep its moon. Aristotle's philosophy also included belief that all heavenly motions were centered on Earth. Galileo's observations showed that Jupiter's moons revolved around Jupiter, suggesting that there could be other centers of motion besides Earth. Sometime after Sidereus Nuncius was published, Galileo noticed something else that made Jupiter's moons even stranger evidence of Copernican model. When he measured the orbital periods of the 4 moons, he found that the innermost moon moved fastest and that the moons further from Jupiter moved proportionally slower. Jupiter's moons made up a harmonious system ruled by Jupiter, just as planets in the Copernican universe were a harmonious system ruled by the Sun. The similarity isn't proof, but Galileo saw as it an argument that a solar system is seen centered rather than Earth-centered, sun-centered rather than Earth-centered. So we can see Galileo's Kepler's laws also applies to moons orbiting planets. In years following publications of Sidereus Nuncius, Galileo made 2 additional discoveries. And from this picture, can you see what one of these discoveries are? Yes, that is sunspots. And you guys know what sunspots is? That is cooler parts of the sun. So how did he observe the sun without hurting his eyes? So the easiest way that we do it today and that Galileo did, you point your telescope So what we do today is, and what Galileo did is, you point your telescope towards the sun, then you don't look through the eyepiece, you put a piece of paper in front of the eyepiece, then the sun will shine through the telescope, through the eyepiece onto the paper, and you can see the sun or moving on the paper. So it's like shining a flashlight on a piece of paper where you can see the light of the flashlight creating a ring. So that's the same idea, and then in that image you can see darker pictures, and that is how you observe sunspots. So if we were on campus, I would have done an experiment to show you that we can observe sunspots. But unfortunately, we are not on campus. Yes, you can see partial and full solar eclipses with the same principle as well. But how powerful was his telescopes? His telescopes were powerful for that day, but not as powerful as the telescopes we have today. So it will be the exact same size as an average pair of binoculars we can buy today, even a bit stronger. So his most profound discovery came when he observed Venus. Galileo saw that it was going through phases like those of the moon. So a question. So yes, you can see transitions of Mercury, but the phases of Venus aren't transitions. So what do you guys think of the phases we see? How does the phases on Venus created? No, it's not Mercury. So yes, then you're correct. Yes, you can use that in the same way to observe the sun. You're correct. So let's investigate this. So if you looked at the Ptolemaic model, if Venus moved in ecliptic centered on Earth, it would always appear as crescent, but Galileo's telescope showed that Venus goes through a full set of phases, proving that it must orbit the Sun, so the Copernican model. So if you look at the right-hand image, Earth's orbit is bigger than that of, larger than that of Venus's. So we have Venus going around the Sun. So when it's on the opposite side of the Sun, it is fully lit. But if it comes closer to Earth, we see parts of the shadow of Venus falling onto it, and that causes the different phases of Venus. Are you all still following? Awesome. So here we can see Galileo's telescope revealed such things as craters on the moon, phases of Venus, and the existence of 4 moons orbiting Jupiter. He demonstrated his telescope and discussing his observations with powerful people, explained how observational evidence could be used to test the prevailing Earth-centered model of the universe. Some of the viewers thought the telescope was the work of the devil and would deceive anyone who looked. Galileo's discoveries produced intense and, in some cases, angry debate. He was condemned by the Inquisition in 1633. And what do you guys see here? Yes, that is Jupiter's moons. So, ladies and gentlemen, I think we are going to discuss Newtonian astronomy in tomorrow night's lecture and finish off the slides tomorrow evening. So I hope you all enjoyed the lecture this evening. So if you have more questions, I will remain active for a few more minutes to answer questions. If you have no more questions, you're more than welcome to log off. Have a great evening, and I will see you all tomorrow night. So Kepler's second law summarized. It means if we move equal areas in the exact same time. So is it possible for us to receive skeleton notes or pre-lecture notes a day or two before lectures? What I will do is I will upload lecture slides a day or two, say a day, say 2 days, 2 days before the lecture. Yes, so we did chapters 1, 2, and 3, and we're on chapter 4. So yes, okay, so mess something up. So if you want to speak about it, the easiest way would be to send me an email. If you would like to speak in person on it, then we can set up a private Zoom, Skype, Google Meets, basically any platform meeting if you want. So yes, the WhatsApp group is active. Just make sure you filled in your details on the Google Sheet. If I missed you on the Google Sheet, just please send me an email with your details. Yes, you're more than welcome if you're okay with it. Then you can tell me, Mr. Phillips. I'm just going to stop the recording, so everyone have a great evening, and I'll see you tomorrow night.